Welcome to this talk. Today I'm going to talk about the support recovery of hard threshold in pursuit. First, let me quickly go through the background of this problem. We focus on recovering a sparse signal X that is t-dimensional. Sparse signals have many applications. For example, in compressed sensing, we have a linear model Y equals A times X plus noise. We aim to recover X using the knowledge of Y and the matrix A. In general, we have to draw D measurements, but if the matrix A is Gaussian and X is S-sparse, it is well known that the order of S times log D measurements are sufficient for sparse recovery. In machine learning, many problems such as sparse PCA can be formulated as a sparsity constraint minimization, and in this case, we are interested in finding a global sparse minimizer. There are many elegant methods in the literature for sparse recovery, like basis pursuit, the lasso, and orthogonal matching pursuit. In this paper, we study hard thresholding pursuit, which is simple and efficient. Given an initial guess xt minus 1, HTTP first computes a proxy PT by gradient descent. The new iterate xt is the minimizer of f of z over the set st, where st is the support set of the top k elements of bt. Our goal is to determine the step size eta, the proxy function f of z, and the sparsity parameter k, such that HTTP recovers the support of x. There are many results showing that HTTP converges very fast. That means given epsilon, after log of 1 over epsilon steps, the iterator of HTTP is close enough to the target signal X into norm. However, it turns out that support recovery is more useful because if a method is able to predict the support, it enjoys optimal statistical rate. So in this light, two recent papers are devoted to analyze the support recovery performance of HTTP. The first one comes from Burchard 16. They consider recovering the true parameter of compressed sensing using RIP condition. Then 16 studied two cases. One is for recovering an arbitrary sparse signal using RIP, and the other is recovering the global sparse minimizer by relaxing the sparsity. In this paper, we established the theoretical guarantee for arbitrary sparse signals, which means our results applies to both compressed sensing and sparsity constraint minimization. Now I'm going to present our main results. For our analysis, we need to assume two assumptions. The first one is restricted strong convexity with parameter little m, and the second one is restricted smoothness with parameter capital M. We define the condition number kappa as the ratio of the capital M over little m. Okay. Our first theorem says if we pick the step size small enough, then HTTP either terminates or it recovers the support of X using order of S times kappa times log of kappa iterations. What is interesting here is that we did not assume the IP condition. Either we did not relax the sparsity, but we show that HTTP still has potential to exactly recover the support. For the X-mean condition, it can also be found in the support recovery analysis of lasso. In general, we can think of this as signal-to-noise ratio condition. This becomes clear if we look at the special case of linear regression. We assume proper conditions on the design matrix, and we can show that the two norm of the top k plus s elements of the gradient is comparable to the energy of the noise. And then we can show that the X-mean condition is basically comparable to the signal-to-noise ratio condition. The weakness of this theorem is that it does not guarantee that HTTP always recovers the support. So sometimes HTTP maybe terminates too fast, and we cannot say anything about the iterate. So we need to strengthen this result by assuming RIP or relaxing the sparsity. So this is our second theorem. It is based on RIP condition, which means the condition number kappa is assumed to be upper bounded by a constant, and we pick step size eta not small enough. So we show that using these two assumptions, HTP recovers the support of X within order of S iterations. We compare this result with previous work. In Burchard 16, they showed the same iteration complexity for recovering the true signal. We show that actually HTP is able to recover an arbitrary sparse signal. In Ren 16, their RIP-based analysis guarantees support recovery of a global sparse minimizer, but their iteration complexity involves a gap of function value between the optimum and the suboptimum, so it is hard to compare T with S. The advantage of our result is that we have a clear dependency on the parameter. Finally, we show that if RIP is not satisfied, we can relax the sparsity parameter K to kappa square times S. And in this case, HTP guarantees support inclusion, which means the support of X is included in the support of the iterate. There is no such result in Burchard 16. In Ren 16, they build the results of support inclusion and support recovery, but the iteration complexity was not given. Now I'm going to state some statistical results. These results are actually well known in the literature, so I just briefly introduce them. Basically, suppose that the data is RID sub Gaussian. Then for linear regression, we can choose the function f as the least squares and show that the gradient of f of x is upbounded in this form. So basically it means if we have sufficient samples, the gradient vanishes and it becomes easier to satisfy the x-mean condition. And likewise for the logistic regression model. Finally, we look at some empirical results. We consider the linear regression model with Gaussian noise. We set eta equals 1 and k equals s. We use the least squares for f of z. We also consider solving the last step of HTP approximately using gradient descent. We use 100 measurements. Here, exact means we calculate the closed form solution for the last step of HTP, and GD-10 means we run gradient descent for 10 steps. Likewise for GD-20, GD-50, and we tune the sparsity from 1 to 50, and we find that the iteration number is roughly linear with sparsity. This agrees with our theoretical analysis. We also investigate the percentage of success against the sparsity. So we find that running gradient descent with 100 steps ensures a good performance. So in practice, we do not have to solve the last step of HTP exactly. We also plot the curve of iteration number against sample size, and we also plot the phase transition curve. Thank you.